This video was produced for those students enrolled in EPO 322 Diesel Engineering 2 Simulation at the California Maritime Academy. This covers presentation 6, which is on motor vessel steam systems. Engineers enrolled in this course have already had a boilers class and know these basic definitions, but we're going to do a brief description of them as a review. The two basic one is fire tube boilers that have combustion gas going through the interior of the tubes and water outside, and water tube boilers which have water through the tubes and combustion gases on the outside, so the opposite. This is actually of a fairly antiquated boiler, this drawing. This was of a coal-fired, and you would open up this door right here and literally shovel coal onto this grate and rake it so it's fairly flat. The ash would drop below the grate, and you open this door and pull on this handle, and there was a steel kind of like a fork that was in the back here that when you pulled it forward would pull the ash towards you and that you'd shovel it out. But anyway, forced draft fan, air comes in here. A modern one would have a rotary cup atomizer and would blow atomized fuel into the space to mix with the air and burn. It burns in these corrugated combustion chambers, furnace, that are surrounded by water. The combustion gases exit the back of the furnace. They hit a refractory wall, going to turn 90 degrees, come up, and then take another 90 degrees, go through these tubes and out the flue. The water level in this boiler would typically be above these generating tubes. This is a picture of a fairly modern one. This is more likely what you would see on a motor ship. And the fire tube boilers for non-liquid cargo is the most vessels is the most common. This type of boiler would be on a large percentage of the motor ships out in the fleet. Now, right here, this is your rotary cup atomizer, and combustion air is going to be coming through this tube. It will be mixing with fuel. It will be burning in the combustion chamber. So this is just a picture of the door opened up for service, and you can see the generating tubes within this boiler. Now, one disadvantage of fire tube boilers is that you cannot soot blow. It doesn't work very well because of these long tubes with the carbon inside the tubes. So one disadvantage of them is that on occasion, if you are burning a dirty fuel, such as heavy fuel oil, you would have to clean these tubes. And it's done with a brush, and the operator stands on this side with and runs a brush all the way down through the tubes. And you would have to do every single tube, and then you go into the back, and there's an opening that you can get in, and then shovel the soot out of the boiler. And this has to be done on a regular basis. And the frequency is dependent on the fuel and how much soot is going to be left behind. Typically, this isn't that big a disadvantage for most motor ships because when they are at sea and underway, the boiler is shut down and you are on your exhaust gas boiler. So this can be a normal maintenance item that is done out at sea. I'm just putting this in as one, it's a fairly common example. Instead of having a horizontal footprint like the one I just showed you, this one has a vertical footprint, and this is your generating tube bank. So those pictures of those tubes I just showed you, that would be going crisscrossing back here. The furnace is spherical, it's steel, and it's suspended in the water. The water level again is going to be about to here. Combustion takes place, hits the refractory wall, go through the tubes and up. It's a fairly common one that the Europeans will use. Okay, so let's look at the advantages. Now, one of the things too is the first listing for an advantage is a boiler reacts slowly to load changes. This is dependent on the application. What we're talking about is motor vessels that that are only a low pressure steam used for heating services and that are unmanned service. There's typically not an operator in the engine room at night, and even during the day, most of these vessels, you're very minimal manned. The engineer who has the watch will actually be doing day work and only occasionally come into the control room to answer alarms or to fill out a log. So what happens is, let's say you're on watch, it's 2 o'clock in the morning, you're up in your room, you got your feet up, you're sound asleep, uh, the alarm goes off, you have to get up, you have to put your clothes on, you got to run 600 feet aft, you got to go 2 decks down, then you've got to go in and answer the alarm and go down into the engine room and find out why the boiler didn't shut down before your steam pressure drops and you lose heat to your generators. Well, the generators would trip prior to the main when you're on heavy fuel oil. If you do not supply steam and keep the viscosity in the right range, the engine would shut down and black out the plant. Well, comparing a fire tube to a water tube, it has a much higher volume of water. It's on an order of at least 10 times more water than a comparable output water tube boiler. What that means is, with that large mass, is that it will continue to percolate, it will continue to produce steam long after the fire shut down. Now, once you get the fire back up, it's going to take quite a while to bring the pressure back up again. But still, it will produce steam for a long enough time that an operator could get down and solve the problem before there are repercussions from the delay. Because they react slowly to load changes, boiler automation can be very basic. The boiler drum contains large amounts of water, simplifying feed water control. This probably is one of the largest factors in being used upon most of these motor vessels. The large amount of water means that if you lose the feed pump, it will be quite a while before the water level drops low enough to affect the boiler in a negative way. In other words, comparing the two, a water tube boiler, if you lose the feed pump, I would say you've got about 5 minutes to get it back. Otherwise, the water level will drop out of the drum and you will start exposing tubes to the direct heat without a coolant, without water inside them, and you will start to degrade the tubes. With this, it would probably be more 15 to 30 minutes before that. And that's a big deal on an unmanned ship. Now, fire tube boilers, I've never seen one. It doesn't mean that they haven't been done, but I've never seen one built over 300 pounds. I would assume most of them about 150 psi would be fairly normal. They're low pressure. Well, for heating services, you don't need high pressure boiler, so that's perfectly adequate. Because it is low pressure, and again, this is because it's low pressure, boiler water treatment is simplistic and it does not require deoxygenated feed water. Once you get above about 600 pounds, your boiler water treatment is starting to get much more complex and you start requiring a DC heater and a closed feed system. So that's a big advantage when the designer is laying out the ship and the systems. This low pressure boiler does not require an expensive closed feed system, and the boiler water treatment is much more simplistic and less prone to the engineers making a mistake. So what's the disadvantage of this boiler? Its efficiency is low. It's very heavy. They're quite heavy for their output. Boiler pressure must be low, and steam flow rates are typically low. So fire tube boilers for producing low pressure steam for heating, they and not having an operator there to watch them all the time, they can have quite a few advantages. But they are specifically not good for running steam turbines. In fact, if you go down on the Queen Mary down in Long Beach, she originally had in her boiler room 32 boilers, and they were pretty close to the picture that I showed you in the beginning. They were cold fire, and they had runners running back aft to fill wheelbarrows full of coal and running it up to the fire room, and then they had firemen that would shovel it into the boilers. The reason they went away from this fire tube boiler, and even the Queen Mary, she's got a steam turbine. So it took 32 boilers. While in today's world, you could produce at least the same horsepower easily with one or two water tube boilers and a much higher pressure for a much higher efficiency. So really one of the driving forces in engineering to change away from the fire tube, because these were the first boilers, was for that reason, to be able to run steam turbines. So water tube boiler advantages: reacts quickly to changes of load, very quickly. All your water is in your drums, in your mud drum down below and your steam drum up above. That contains the vast majority of the water. What water you have in the heat exchangers, in your generating tubes, in your water walls, the water has a lot of surface area because the tube is surrounding a small quantity of water, and you have the gas going around the outside. It's a very high heat transfer. That boiler will react very quickly to changes in load. Can produce high pressure steam suitable to drive steam turbines. Boiler can produce high steam flow rates. Compact, light, efficient. Disadvantages: well, if you want to get the advantages of reacting quickly to changes in loads, you better have a sophisticated combustion control to be able to deal with that. Boiler steam drum water level is critical. Loss of feed water will quickly destroy the boiler. Absolutely. You need you need a very, very competent automation system to be able to deal with this without an operator. That doesn't mean that they haven't been built fully automated, because they have. One of the ships that I used to be on, the Kenai Sea River, is running that. When I was on it, it had a 24-hour watch, and that had been changed, and now it's fully automated. No one in the engine room in the evenings. But again, it's much more of a worry, and you need a much more competent automation systems with a lot more safety features to be able to deal with that. Now the last two, boiler requires sophisticated water treatment and boiler requires deoxygenated feed water. I need to put in a little caveat on that. In that's only if it's high pressure. It's only if it's high pressure. Now in the simulator, it is a water tube boiler, and it's running at typically top about 16-18 bar. Well, that's relatively low pressure, and because of that, it does not require deoxygenated feed water, and it does not require sophisticated water treatment. These last two things are dependent on pressure. The higher the pressure of the boiler, the more it is subject to oxygen corrosion, the more it's subject to scale and other problems and has to have a much better regulated water treatment. So this is a close approximation of what you have in the simulator. Very close to what you have on the steam sim. In fact, the simulator is a ultra-large crude carrier. And the boiler on it, even though it's a motor ship, the boiler on this tanker has probably very close to the steam output of both boilers. This one boiler on the diesel sim would have approximately the same output as both boilers on the steam sim. The reason for that is you are using steam cargo pumps. Steam cargo pumps are relatively compact. They can produce high amounts of power, and they are used to remove the cargo from the tanks and pump them ashore when you're discharging cargo. I'll give an example. I'll go back to that Kenai again. It was 120,000 deadweight ton, had about 1 million barrels of crude on board, and you could pump that 1 million barrels of crude in less than 12 hours. So the name of the game, and think about how much, when you've got 1 million barrels of crude, how much money someone has invested in that cargo. And they don't make money having it sit on the ship. They want it discharged ashore, and they want that ship back out and going up to pick up another load. Well, like I said, these steam cargo pumps are fairly small and compact, but they're typically only about 2 stages, compared to a main engine, which is, I'm just guessing, but say 16 stages. So there is a lot of heat from a cargo pump that is just being dumped into the condenser. They're not efficient at all. That's not the point. You're only running them for 12 hours. And I want compact. I don't want to have a bigger engine room and be able, and then, which means I have to carry less cargo. So they use a high volume of steam. Going back to the Kenai, 24,000 ship horsepower main engines, about 8,000 in 4 cargo pumps. When the cargo pumps went on, this demand on the boiler was fairly close to what the steam demand when that ship was at sea under full load. So that 8,000 horsepower, when it's up and running at maximum capacity, was very close to the same steam demand of that 24,000 horsepower main engine. So we're talking big boilers. Now, the reason that this has been done too is the compact high horsepower pumps, but also the fact that I can pull the flue gas off of this boiler, clean it through by putting it through a scrubber, and use it as an inert gas to put in the tanks, in the cargo tanks, to prevent explosions. So I can use the boiler to burn the oxygen, that 21% oxygen. It'll burn that oxygen down to typically at sea speeds and out at sea, about 2% oxygen in the updraft. I can remove that oxygen. I can take that flue gas, and I need very high, these are big ships, the very, very large tanks. I need a high volume of gas. It will produce that gas, and I can recover that waste heat to run the steam turbine. Some of the modern ships are going to electric motors, which means they have to be a high voltage system to run high horsepower electric motors like that. You're up between, Polar 6.6 kV, BP is 11 kV, 11,000 volts. Now they don't have this big boiler, so what they do is they have a separately fired inert gas generator that just burns fuel to remove the oxygen from the inert gas, but there's no heat recovery. With this system, you had heat recovery. So anyway, on this is your economizer tubes. These are your generating tubes. These are superheat tubes. These are your screen, your water walls. Here's your burner. Forced draft air comes around the casing through here. The combustion takes place in this area, goes through your screen, superheater generating, and out your economizer. Now we're going to be lighting off a boiler from cold. Again, this is a very large boiler. It has to be brought up slowly, specifically from dead cold. So what we're going to do is we're going to light off with a minimal, absolute minimal fire. It takes 4 hours to bring this boiler up to full capacity. You're not to see you're not to see any pressure, anything coming out the air cock for at least an hour. And if you did, you shut the burner off. Wait for the hour to have transpired and then light it back off again. The reason being for this is the superheater. Now, a lot of the old Navy books will talk about the screen tubes protect the, and that can get you, that thought process can get you in trouble. It's really a misnomer. These screen tubes were put in for another purpose. They are there actually to help regulate superheated steam temperature from low load or changes in load, from like going from low load to going to a high load. I always want my superheat to be 940 degrees, not 910, not 950, 940. Because if I drop the superheat temperature down, I lose efficiency and I lose horsepower output. If I go above 940, then I'm going beyond the capabilities of the metallurgy, and I'm going to be damaging the superheated tubes. So by putting in, and they can be between 1 and 4 layers of these screen tubes, that helps shield the superheater from the radiant heat. In other words, it protects them from the radiant heat. That's not to protect the tubes. That by protecting them from the radiant heat of the fire, which changes in the firing rate, that would, excuse me, I should take that back. The amount of combustion gases going through the generator tubes will change with the firing rate. The radiant heat that's striking those tubes is always typically the same. Because of that factor, you would get, if you didn't screen them from the ultraviolet light, then you would have a temperature changes from low load to high load. And you can usually see the superheated tubes very easily between the screen tubes. They may be more than an inch apart. So the main thing to think about is the superheated tubes, by definition, have to be totally empty of liquid. They can never have liquid in them. If you did get liquid in them, then the boiler chemicals would scale out, cause an overheated tube, and it would rupture. They always have to have strictly either air on startup, or more typically when you're running, then they would have steam inside them, and you have a gas-to-gas transfer, not liquid to gas like we do in the generating tubes. That means that these superheated tubes are very, very subject to overheating and failure if you do not have a competent boiler operator. It is a high concern in a motor ship. Now, so on light off, typically I'll ask the students, what's protecting the superheated tubes? And they'll say, well, it's the superheater vent. And I'm going, well, you have no steam. There's no flow. You just lit off. The answer to this is nothing. There is nothing protecting the superheater tubes on light off except for the fact that you have a minimal fire, so the average combustion gases in the furnace are low. When you light the burner off in the simulator, you're going to light off at, say, like 15%, but then you're going to, that's so I can have more assurance that it will light. But once it's light, the answer to this is you drive the flame down, the size of your flame down to its absolute minimum that you can do to and keep a flame. And most of the time, it's slightly too much, and you probably will have to shut the burner off because you'll start seeing steam coming out the air cock, and you just shut the burner off. Okay, so on the simulator again, use that drawing to think about this boiler. Here's your superheater, and in this case, by the way, these two graphically, they move this up, and that is the same as up here, okay? So that's just kind of they wanted to tie in this graphic drawing to the graphics of the system. So the steam's coming this way, going through the tube, coming out, and coming this. You notice there's no valve between the dry pipe and the superheater, and that's very, very important, and it is definitely in all the regulations to prevent overheating of the superheater. That what does protect the superheater is steam flow. You want to have every bit of the steam coming out of this drum going through the superheater, because that steam flow is what's protecting it and what's transferring heat. Then from the superheater, it's going to go down and into your desuperheater, come out, and through your desuperheated steam stop. Now, the other thing on this too, if I'm ever to ask you what is the purpose of a desuperheater, there's only one answer I accept, because that's really what it's there for. It does some other things, but that's why it's there, and that's only why it's there, is to protect the superheater by ensuring all steam flow is through the superheater. Originally, with the graphics, they had, even though they'd modeled it correctly, whoever did the graphics had made a mistake, didn't show the desuperheater, and had the saturated steam going directly to saturated steam services. If that was actually the case, you would burn up the superheater the first time you lit off this boiler. Because until you put on a steam turbine, I wouldn't have any superheated steam flow. All of the steam would be going to saturated services, which would mean there's nothing going through the superheater, and it's going to melt down. And the one important part to think about this too, okay, so why don't I just take superheated steam and go to all my heating services? Why am I taking that superheated steam and going through the desuperheater, which, by the way, the desuperheater is typically, say, about 2-inch pipe, 2 to 4-inch pipe, running down the bottom of the drum and making about 3 or 4 passes and then out again. So all that's happening is that energy from the superheated steam is being transferred back into the water in the drum until it reaches equilibrium. So you really haven't lost anything by superheating that steam up, because now that you're going back to saturated, you're just transferring the heat back into the drum. The reason why you don't use superheated steam for saturated services, it is at a high disadvantage. Go look into your tables and look up the coefficient of heat transfer of superheated steam. It dramatically drops. The heat transfer drops with superheated steam. And it's a very simplistic answer for that. Superheated steam, the water molecules are moving at an accelerated rate. They are not in contact with the container for as long as saturated steam, and they tend not to transfer heat. So you don't want superheated steam for saturated services, for heating. Absolutely do not want it. So if you see a superheater, go find the steam turbine. You only have superheated steam for steam turbine, because a steam turbine will directly convert that heat into usable power. Now here is your air cock. The reason for this, by the way, we're lighting off and the drum has no pressure on it, it's cold, and with that being open, realize that there is air inside this drum now, so there's 21% oxygen in here. If I didn't vent that air off, that atmosphere off, that oxygen would get incorporated into the feed water. So what I'm going to do is wait until that there starts to build steam pressure, and that's going to be pushing the air. The steam that's being created will push the air out the air cock, and once you see steam coming out, then you go ahead and close it. On shutdown, you would open that up to prevent the drum going into a vacuum when the steam collapses. The reason for that, the reason that you're worried about that, it's not going to hurt the boiler per se. I mean, this drum, is typically meant for high pressure. But what can happen on your drains, for like your headers, right, or your blowdowns, there's a chance that those valves can leak, and when you draw a vacuum in the drum, that could pull unwanted water out of your bilge or from the sea into the boiler. So you get down to say 25 pounds or so, you want to open up the vent, or the air cock, so that steam is coming out and you don't have to worry about pulling a vacuum. Superheater vent, for this scenario, we're going to leave it open all the time. And again, think about, I want steam flow, so I'm going to leave the superheated vent open, and I'm going to want to leave the desuperheated steam stop open. And here is my drain for the services, and I would leave that open until all the water had been removed and I was getting steam output. Again, I want as soon as this boiler starts producing steam, I want flow through the system to protect the superheater. So boilers are typically, another designation is natural and forced circulation. Natural circulation is the D-type boiler, where as exhaust gases go, and these would all be tubes, right? As it goes through this generating back, the forward tubes, the heat transfer would cause steam bubbles, makes the liquid lighter. So water will come down from the back tubes into the mud drum, and then that rising water comes up, and then the steam is separated in the steam drum. We won't talk about critical because that's not for, but we will talk briefly as an example of forced circulation is the Clayton boiler on the Bear. That is a forced circulation boiler. It's a little bit different in that your feed pump here actually goes to the tube. So the circ pump is gone, and on our system the feed pump comes out, goes right through the tubes, and then it goes into the steam separator. The thing about this one, with a forced circulation, you have a pump that's forcing water through your tubes. If something happens to your feed pump, this boiler will burn up almost immediately. In fact, it has 3 totally separate, redundant safety systems to shut this boiler down almost instantaneously on loss of feed pump or low output. So I have a pump that's forcing water through the tubes rather than natural circulation. So on this simulator, we just took a look at the steam side, or excuse me, the oil-fired boiler. Now we're looking at the exhaust gas boiler that's up in the stack. And in this case, this is a forced circulation boiler. Right? I've got my generating tubes up here, and they are being supplied water from the circ pumps. Let's go back a little bit because I forgot on that. All right. So I have these 2 circ pumps right here. We'd only use one at a time, and it's going to draw water out of the mud drum. It's going to send it to your exhaust gas boiler. That returns back and into the steam drum. So when you think about it, this boiler has 2 sets of generating tubes. One, when you're firing it on an oil fire, this set of generating tubes here. When the boiler is shut down and you're out at sea and the main engine is on, then it is being supplied from the generating tubes in the exhaust gas boiler. By definition, this is a combined cycle plant. We are raising the efficiency of the entire plant by recovering waste heat. And again, this is where steam's going. Steam is not used as much anymore as a methodology for producing the main body of power. In other words, vessels with steam propulsion turbines have pretty much disappeared from the industry worldwide, and this is also happening with power generation shoreside. But let's talk about the combined cycle gas turbine plant across the water in Crockett. That is a very large plant, and it has a gas turbine that burns the fuel that is led into a waste heat boiler. Now, that fuel is typically, over there is going to be natural gas. But what I want you to think about, yes, the gas turbine is driving a shaft to generate electricity directly, but it's only about 35% efficient. Gas turbines are the least efficient prime mover out there. They're the least efficient. Yet, because it has a 1,400-pound boiler, and instead of a burner, I'm using a gas turbine now. And I'm burning that fuel, and I'm putting it into that waste heat boiler. And then that steam produced on the waste heat boiler is running a generator. So you're jumping from 35% efficiency to 60% efficiency, and 60% plant efficiency is about as good as you get in our world. So because it's combined cycle, I can run that gas turbine and have high efficiency. Now, the other thing while we're here and on this page, I wanted to point out the dump. This dump valve, when you're out at sea, if the steam turbine is producing, step back. When you're out at sea, if the boiler drum is producing more steam than what you need, in other words, I'm picking up heat solely. I don't have a fire. I'm in the boiler. I'm solely picking up heat from the main engine. If the steam pressure gets higher than what I need, I can simply have it go through a pressure regulating valve and dump it down to an auxiliary condenser. Or an atmospheric condenser, I'm sorry, not auxiliary. The reason for that is if I'm just using it for heating services and I have more than I want and I have no other use for it, then I may as well just dump it. Now, in this particular installation, and we do have a steam turbine that is used to take that what we can't use for heating services, we put into a steam turbine to generate electricity. So again, this plant, just like that gas turbine, does have a steam turbine to recover waste heat, and this has similar efficiencies on the plant. In fact, we may be a little bit higher because we're also using other energy from other sources. Now, you see the superheater down at the bottom. That means that there is a steam turbine in the plant. These dampers, this was the Europeans were using this to regulate steam pressure instead of the dump that I just said. Makes almost no sense to me. What would happen is, like right now, this bypass is closed, so all the gas would be going up through these tubes and generating steam. Well, I've got a steam turbine. I'm combined cycle. Why would I ever want to bypass that? The other thing on this is by regulating gas flow and bypassing some of the main engine gas around the exhaust gas boiler rather than through it, slows the speed of the gas upward movement, and it's more likely for that to settle down onto the tubes, and you're more prone to an exhaust gas boiler fire. So in this scenarios that I built, we are not really using these. We'll either like fully open or fully closed. They would also be a huge maintenance headache. So we see a superheater, and the gas flow, right? The exhaust gas is coming up this way, so the hottest to the coolest is moving up. And then on the water, the coolest is coming into the economizer, then going to the evaporators, and then going to the superheater. So I can get more heat transfer. It's counterflow. And if I have a superheater, I have a steam turbine. One thing I want to bring up is that on motor vessels, your feed tank is a combination feed tank, contaminated drain tank. Most ships have a lot of contaminated services coming back. Any of that could be contaminated with lube oil or fuels from heating of the lube oil and heating of the fuels. That oil would tend to float to the top of this first segment of the tank. And then I have a diaphragm that is basically extends down the tank and separates these two, except for a small gap at the bottom. So the water has to go down, around, and up, and the oil would stay on the top. That's the point. Make sure that you check this on a regular basis and that any oil is skimmed off. There have been cases before, especially like if you'll get a broken from vibration, a broken heating coil in a tank, where this can literally fill up full of oil and the oil blow out and over and into this system and charge your boiler with fuel oil. God help you. You'd want to find it before that. So always, and one of the problems on the Bear, since we do very little contaminated services, we don't watch it enough. In real life, you watch it. So anyway, that can go underneath, up through some loofah sponges, and then this weir sets the height of the water level in both tanks, because they are connected here on the bottom, and then overflows into the feed section. So this is a typical looking one on board a vessel. This is, by the way, is your atmospheric condenser, where and this ship did not have combined cycle. It did not have a steam turbine. So if the pressure in the steam drum gets too high out at sea when you're on waste heat recovery, all that happens is the excess steam is dumped into this unit, and then the water transfers into the tank. This is just saying again that what we're doing as far as combined cycle. Now, this is from Burmeister Wayne, and it's looking at the breakdown of the waste heat. And not just waste heat, excuse me, but also how much power I'm producing. They're claiming about 50% power output from this. In other words, 50% of the BTUs coming into this internal combustion engine is being converted into actual power. It's slightly less than that because down here you don't see any of the losses for pumping jacket water, for pumping lube oil, and there is some. I'm guessing a little bit, but I think it'll be about 3%. So you're probably about 47% efficiency. Was really as good as you get by itself without waste heat recovery. Now, so what can we recover some of that heat and improve our plant efficiency? Lube oil cooler, it's about 3.3%. Low grade heat, you're only down about 40 C. It's not enough. So you really can't recover this little bit about heat. I've never seen anything where they recover from a lube oil cooler. Jacket water, 5.8%. Yeah, we can do that. We can recover that for our evaporators. And there are some ships that will use this for heating of the house. They'll have a heat exchanger and either use a water as a medium, or in some cases I'm hearing they're using a thermal oil. But here's the big boy, exhaust gas. That's a lot of heat we can recover. Now, the more efficient, the bigger the turbochargers, the more waste heat is going to be, or the more of this heat is going to be taken up by your turbo to produce boost for the main engine. So the newer engines with these big turbos, there's less heat for recovery. Typically anymore, I think you're above about 60 megawatt prior to getting into where you could efficiently do combined cycle. But there's quite a few ships out there in that power range. I've been on a Maersk vessel that actually had it had a steam turbine coupled into a reduction gear driving a generator, and also a, believe it or not, a gas turbine coupled into and fit in, just kind of like with our main engine, right, where you've got the two inputs into your reduction gear. It was the same type of a thing with a steam turbine and a gas turbine. All waste heat. They would bypass some of the gas around the turbochargers to go to this power turbine. And that produced 3 megawatt of power at sea. So that from waste heat, they could produce more power for utilization in the plant than the total capacity of the Bear. Remember, the Bear, you've got 3.9 megawatt generators. And then you typically do that with an exhaust gas boiler system. Now, air cooler, 14.6. You can recover a portion of that too. It's not a lot of savings. It just really depends on with the designers as far as current pricing of fuel costs, and they have to amortize that over the life of the ship and see if it makes sense. But there are some cases where they are using this. Exhaust gas boiler types. You've got water tube and fire tube. Water tube is more common. They look like economizer tubes. They're up in the stack. These are what they're calling guild tubes. Would be the most common. And again, this is up in the stack. You've got exhaust gas from the main engine going past, transferring heat into this, and then you have a circ pump circulating water. And your boiler drum is going to be elsewhere. It will either return to the auxiliary boiler if it's large enough. If the auxiliary boiler is not large enough, you may have a separate steam drum for the exhaust gas boiler system. Fire tube boilers. Basically a big drum of water up in the stack. It doesn't need, its advantage is simplicity. Needs a feed pump to pump water into it. Does not need a circ pump. The exhaust gas from the main engine go through these tubes. Steam is produced, and that's let out as saturated steam. With this, the one disadvantage is where a water tube boiler or a water tube exhaust gas boiler, you can blow tubes very effectively to clean it. These you cannot. So on occasion, you're going to have the extreme pleasure of crawling in underneath the or above the exhaust gas boiler and running brushes down through the tubes to clean them. If you don't, you're subject to an exhaust gas boiler fire. Now, while I'm here and thinking about it, let's talk about that a little bit. As the gases move up through that tube, we're burning a very low-grade heavy fuel oil today that produces a large amount of soot. You need the velocity of the gas running through the boiler to be sufficient to carry it out, and then that way it can drop it down on the main decks and irritate the mates. Right? You don't want those heavy particles, the flow rate, not to be high enough that they escape and then just fall back down and lay down on these tubes. Because then you'll form a layer of carbon on the tubes, and which, if it gets hot enough, can ignite and cause an exhaust gas boiler fire. You are pushing exhaust gas past it, and that exhaust gas is a much higher oxygen content than on a boiler. Out at sea, a steam boiler runs about 2% excess air. On modern diesels, you are running a lot of the boost produced by the turbos is used to cool the exhaust chamber, the cylinder. So you're up around 14% oxygen, which is absolutely high enough to support combustion. You typically get exhaust gas boiler fires during maneuvering, but it can happen at any time when the engine is running. You will know if you get an exhaust gas boiler fire. Typically, one of the things the mates will start reporting to you that there's a lot of sparks coming out the stack. The turbos may start to surge. Your exhaust temps are going to go up, and there's usually a pyrometer in the stack that will indicate to you that there is a problem. Typically, your reaction should be, of course, to notify the chief engineer and the captain that you believe that the exhaust gas boiler fire is present. When safe, they will shut down the main engine. I would typically suggest that you have tarps to wrap around or canvas made to put over the top of your air cleaners into your turbos so that you can stop airflow through the exhaust gas boiler. That's a primary, right? You want to starve this fire of oxygen is your primary fight. If you have a CO2 system to do that, then you can deploy the CO2. I haven't really seen that as often. Now, the next thing about this is keep an eye on the casing, and if it starts getting really hot, you have to cool it. What you're worried about is that the fire could cause an opening in the casing, allowing air in. Keep your circ pump on. If you're a water tube type, you keep your circ pump on. If you are on a fire tube point, you make sure that they maintain the water in the drum. If you don't, then that fire will much more readily can melt down these tubes, and even more than that, can actually cause the metal, the steel, to burn, and you'd have a metal fire. And you cannot deal with a metal fire on a ship. So maintain your flow of the circ pump or boiler water level in the fire tube type to maintain cooling to the tubes. But specifically on this, watch your circ pump discharge. And if you would see that pressure to drop down very suddenly, the tubes have been holed, and you're worried now that you have a metal fire, you have to shut down the circ pump, and you have to shut the inlet and outlet return from this system, because now you're worried about pumping water to a metal fire. It will break down the H2O into H and O2, and you're feeding hydrogen and oxygen to that fire. Absolute worst case scenario. So how do you prevent exhaust gas boiler fires? You've got to make sure that you're looking at the pressure drop across the exhaust gas boiler on a regular basis. And you have to know what's normal. And if you look in the operating manual, it will tell you when you have this much change, then you have a problem. You're going to have to blow on the water tube. You're going to have to blow tubes on a regular basis, daily typically. You're blowing tubes. On your fire tube, you're going to run brushes through that on a regular basis to make sure mechanically that you're cleaning them. You also have to do visual inspections at least once a month to visually look at these to make sure they're staying clean, and you water wash them if there is accumulated soot that needs to be removed. You have to maintain these, otherwise you're subject to these devastating fires. And the thing about this too is if you were to get into a metal fire in the exhaust gas boiler, so much material would be dropping down from that fire and most likely would get into your turbochargers. You'd be very difficult for me to see where you would be able to get underway if the fire was that devastating. So for the typical steam system, well, that most motor vessels would have, that's just for heating services, right? We don't have the horsepower output to have enough heat to run a combined cycle. This would be the plant that you'll typically see. You'll have some sort of an oil-fired boiler for import use, and then that would supply steam to all your services. If out at sea, then you have a circ pump that's just going to circulate that through the exhaust gas boiler, and the steam from that then would again go out to your services. So again, two boilers, either natural circulation fired or forced circulation out at sea. You have more than what you need. You're going to dump the excess to this atmospheric condenser, and then here's your feed tank and your feed pumps. On ours, one of the things here is, so you notice you have the main feed pump and you have the auxiliary feed pump. The main feed pump feeds into the economizer and then into the drum. The auxiliary goes straight to the drum. So this one is designed for combined cycle out at sea. This one, by the way, and it's really used in port, this one is for running your cargo pumps. The cargo pumps, typically at sea and in port, just heating services. Let's actually just say it in port and heating services. Like through most of the scenarios that you're going to go on this boiler is only maybe using 2% to 5% of its capacity. It's just kind of idle. When you were to run the cargo pumps, you would be putting this up to 85 or 90% of its capacity, and I would have to use this bigger pump, and you also have a bigger condensate pump. So this is designed for, and it's a very small in comparison, for heating services and combined cycle, and then this is designed for running those big cargo pumps. And we have circ pumps that circulate water through the evaporators with their generating tubes right back to the drum. The feed pump goes into an economizer, and we have a superheater for running that steam turbine. Now, the other thing I want to point out is you notice that we're heating the feed tank. There's a specific reason for that. The water goes through the feed pump and into the economizer. Now, we have to have the water coming into the economizer has to be above the sulfuric acid dew point. In other words, we don't want the sulfur in the fuel to be able to combine with the water, the moisture that will be present in the flue gas, and condense out to sulfuric acid, because that sulfuric acid would very, very quickly heat up or eat up my economizer. So we will have to heat this tank to make sure that the incoming water would be high enough to prevent that. Now, if you were going to natural gas, a clean fuel with no, or LNG with no sulfur, we wouldn't do this. We'd want to get that economizer pick up absolutely as much heat as we could, and we would drop the flue gas down as low as we could. We want that heat. The problem with heavy fuel oil, and it's a high sulfur fuel, we can't, because the acid is so detrimental. So this is a typical feed pumps. These would be multi-stage, because you have to be able to take from atmospheric pressure, go up to the same full or above drum pressure. And again, the other thing too, I should open, this is an open feed system, right? This is a typical open feed system with the feed tank vented to the engine room. And these are your circ pumps. They're basically single stage and much simpler in that what you're really doing is just forcing water through your generating tubes. So you only have to develop enough pressure dependent on the height of the force of your generating tubes in relationship to the height of the steam drums. So again, you will not typically find forced circulation like we have on the Bear, except for these exhaust gas boilers. So typically, most ships, container ship, only heating loads. What you're going to have is an oil-fired boiler of some type, and typically that's going to be a fire tube type, producing steam and port. And out at sea, you will be producing steam through your exhaust gas boiler, and the oil-fired will be shut down. If your oil-fired boiler is big enough, the exhaust gas boiler will use its steam drum. If not, it may have its own separate steam drum. And then if you're getting into bulk liquid cargo carriers, right, an oil carrier, tanker, if they are using steam turbine cargo pumps, you will typically utilize a water tube boiler and a similar system. If you have a large enough engine and you're producing enough heat in your exhaust gas, there's enough heat transfer to the exhaust gas boiler, and typically I think this, I don't know the exact dividing line, but it's about 60 megawatt, it seems to be. Then you're going to go into a combined cycle and have a steam turbine that will take that the heat that you have above what you need for heating services and use that to generate electricity. So this would be, this is actually an older exhaust gas boiler, in that it will get into that is, this is a typical exhaust gas boiler. In this case, this is your economizer, these are your generating tubes again, and this is your superheater. Similar to what we have here. Again, counterflow. So in this particular vessel, it's a fairly efficient, these were the C10s. Behind these tubes, you would see the handholds for a water tube exhaust gas boiler. And then these are your SIP blowers. By the way, on these, with your SIP blowers, this particular engine, there was not enough heat available to run steam steam soot blowing. They just there's not enough steam production, so they actually use start air as the medium instead of steam. So that's a closer look. And again, if in doubt, blow tubes. Keep them clean. Now, right here, what's going on is they've moved the superheater. Instead of where we saw it before, they've moved it up instead of the economizer. This is going to drop your efficiency of your plant. The reason I bring this up, the reason they don't do that is they are so worried that untrained engineers could burn up the superheater if it's down here, because it's exposed to the highest temperature gases in the boiler, and which are well above the melting point of steel. And you have, so down here you can very, very quickly, within 5 minutes, destroy a superheater. Well, now that if I move it with the economizer, this is the lowest temperature. So what happens is it's going to be giving up its heat as it goes through the generating tubes. Back here, this gas is well below the melting point of steel. It's quite low, actually. And as it goes through the superheater, that will pick up some more heat. You're not going to get the highest superheat temperature. That's going to decrease the efficiency of the steam turbines. And you don't have an economizer now, so that's going to decrease the efficiency of the entire plant. This is going to cost the company some money. They do this because they're so worried that their operators are properly trained. So think about that one. All right, combined cycle. Here's the steam turbine that I'm used to pick up the extra heat. So with this, I have, I still have, in this case, an economizer. So the feed pump is going to go through an economizer and into the drum. Here is my evaporators. And then I also have a steam turbine and an atmospheric condenser. So again, this is by definition combined cycle. If I take my saturated steam, put it through a superheater, and then use that to build for a steam turbine. Some of the ships I've been on with this system, you basically, your oil-fired boiler is shut down out at sea, plus your auxiliary diesel engines, your generators are shut down, and you're strictly running on this steam turbine waste heat. So think about that, even like on the Bear, how much money we could save if out at sea all your electricity and all your steam heating was produced from waste heat. Now this is an example where you're trying to pick up the maximum amount of heat recovery from the system. So, and here's my feed tank, open feed tank. I've got a feed water that is going through, in this case, the charge air cooler. Kind of like on the Bear, where you have the two charge air coolers, one in front, one behind the other. Now I can pick up some waste heat here, and I can put that into the economizer and pick up more heat in the economizer and then into the drum. So I'm doing waste heat recovery here, plus I am bringing up the temperature, so the temperature will be high enough to prevent getting into trouble from acid formation in high sulfur fuels. In this case, they're still a little bit worried about that. So what they're doing is they're taking some of the hot water and feeding it back into this loop here after the circ pump, and it's temperature regulated to maintain this. If I'm running at low loads and this is not high enough temperature, at low loads they would feed in some hot water to prevent the acid formation. And then here is, so my saturated steam is going to go through a superheater and into a steam turbine. The other thing I'm going to mention here, on this one, this also has the steam dump here. But on this type of system, you can, at sea, you control boiler drum pressure with load on the generator. So let's take our simulator. Our simulator, we have a shaft generator on the main engine, and we have a steam turbine. It's fairly modern, very efficient engine. I have a limited amount of waste heat available that I can use for producing electricity. It's not enough for the whole plant. So you're going to have the shaft generator on and this on at the same time. So what happens is if my boiler pressure starts getting high, I will increase the input to the governor to increase the load on the steam turbine, which means that it will demand more steam flow to the turbine, which will drop the pressure, and it will produce more energy, and the shaft generator will have to produce less engine power, which means more is going to the prop, and the engine, the ship would speed up a little bit. So this is just supplying a portion of it, and I can change the load on this generator to control my boiler pressure. All right, the next thing I want to talk about is pinch point. Counterflow. So this is the exhaust gas going up through the through the stack, through these heat exchangers. And this is the water at the top going through the economizer, boiling in the economizer tubes, and then being superheated in the superheater. My delta T here keeps getting less until where it's at its minimum. It's called the pinch point. Pinch point is where the delta T between the exhaust gas and the steam is at its lowest point. Now, I think you would agree I'm going to be transferring a lot more heat than I am down here. So we're going to pick up some heat here in the superheater, and we're going to pick up some heat here in the economizer. But as far as boiling steam, right where the delta T is the least, it's called my pinch point. On some systems where they want to pick up more heat, they will go to a dual pressure system. The dual pressure system has two saturation temperature pressure relationships because of the pressure difference. So I have a low pressure drum and a high pressure drum. What that means is that I will have two different saturation temperatures, which equate back to this shelf here, right? That's why this is flat, because the water is boiling into steam, and so that temperature is not going to change as long as material is changing state. But with this, I have two of those relationships, and I can increase my delta T. Now on these, I have a low pressure boiler with its own circ pump, with its own evaporators going to low pressure services, heating services. I have a high pressure boiler, right, going to a high pressure evaporator, which goes through the superheater, right, which goes through the superheater and into my steam turbine. So the high pressure is used for the steam turbine, the low pressure is used for heating services. And what that does is it gives me two saturation temperatures and two shelves. So like here, okay, here's my pinch point. I'm not going to be transferring much heat, and I want to get as much as I can, so then I drop down on the low pressure side. Now my delta T is increased, and here's my secondary, and if I still have, I'll pick it up in the economizer. This is when they want to pull every last drop of heat out of the exhaust gas boiler system. So it has two separate drums, two separate circ pumps, supplying steam to two separate systems. This would be, this is one of my first ships I was on, the D9s. This is the steam cycle for them. Here is your steam separator. By the way, steam drum, steam separator. For some reason, when they're horizontal, they call them a steam drum. When they're vertical, they call them a steam separator. But here's my oil-fired boiler. It had a separate, because this was not big enough, and this was a fire tube. They had a separate steam drum for the exhaust gas boiler. And it had a low pressure system, and it also had, this was a two system, low and high. And it had a steam turbine with a main condenser. It had air ejectors. It has feed pumps, and an open feed tank, kind of like a steamship, doesn't it? All right, this is the last one we're going to talk about, and this is where I want to get the efficiency. The Europeans use this. This is where I want to get the efficiency of a high pressure boiler. Well, high pressure boiler, I got problems. I need a DC heater. I need a closed feed system. That's not an inexpensive item. That's an expensive item. Well, this is what they came up. This is your high pressure, like 1,200-pound boiler, producing saturated steam that's going through a heating coil in the secondary steam drum, which they call a steam-to-steam generator, and then it flows back into the oil-fired boiler steam drum again. Natural circulation here, right? The steam goes up, and this steam drum is probably within 5 feet of the oil-fired boiler steam drum. So these lines are fairly short, and the gas goes up, heats the water in this drum, condenses down to liquid, and then flows back to the drum again. So that it's a closed loop system. It's closed loops where there's almost no chance of leakage. This is all welded together piping. There is no leaks in this system, which means I don't need a feed pump, and I don't have one. I have makeup feed pumps where I could add water, initially water to get the drum at the mid-level, and slowly over time, if I did have some leakage, I could put a little bit more water in. But I want you to understand is normal operating, there is no feed pump on this system. It's all natural circulation. The gas goes up, changes state, and then flows back. And it's going to what they're calling a steam-to-steam generator. Think of your contaminated vat on the steam system, on the Haven, right? You got a dry pipe here. This is full of water. I have the steam coming in, transferring heat into that water to boil it. As it changes state and goes into a liquid, then it flows back to the drum again. So I can have Drew come in, initially set up the chemistry on this boiler, and that's my whole cycle right there. So I have a closed feed system. I absolutely have a closed feed system, and I didn't have to put in any expensive DC heater and anything else. Now, this is a low pressure system, and it requires fairly simplistic feed water control, and this is just like the other ones that we're talking about. Okay, so with this, what's going on is I want the efficiency of a 1,200-pound boiler, and I could go to the additional expense of putting these steam-to-steam generators, so I could run these 1,200-pound boilers. I don't have to worry about deoxygenated feed water because this is a closed system, and it was initially charged with hydrazine. Nothing should change, and my chemistry shouldn't change. So again, just as a quick review on a combined cycle, one of the more high efficiency out there. To get that high efficiency, you may have a low pressure and high pressure system. That's so I have two different saturation temperature relationships, which will increase my delta T, and I can pick up a little more heat. I can have a steam turbine that would, any heat above what I need for just heating services, I can use to combine cycle to produce power for the plant. In this case, what I'm doing is I'm using heat from the charge air cooler, right? I'm recovering that heat. I'm recovering heat in an economizer. And remember too, it's not shown here, but I'm recovering heat from my jacket water. So this is an example of one where they've tried to get all the maximum amount of heat to increase plant efficiency, which is the name of the game. Alrighty, that concludes this presentation. I hope it has been helpful. Thank you.